Okay, so let's get started. And in the previous class, we were looking into concepts based on impedances, right? Concepts based on um, input and output. Specifically, we saw an example as to how Z0 is calculated, that is your output impedance. And we also saw, the importance of looking into the data sheet and how the values can be extracted. Most of the time these values will not be given, okay, so which means we will have to refer to the data sheet. Okay, so probably for your exam point of view, we will provide the data sheet so that you can refer and you can extract the values and use it in your problems. Okay, so I will make sure that this data sheet is allowed in your examinations for your semester end examinations. Okay, so yeah, so we were looking into impedances and we derived few formulas. We looked into few formulas and some circuits, right? So moving on with our discussions, we will see what is slew rate and frequency limitations. Right? So we have seen, this term slew rate, and we have seen frequency, right? So what can be the limitation, okay, and how it impacts the circuit, right? So we will just look into it. If possible, please try to make note of this circuit here. It's going to be helpful. So let's start with the slew rate. The slew rate of an op-amp is the maximum rate at which the output voltage can change. So it's nothing but, how much can there be a change in the output. Now, an output, as we all know, cannot be constant, right? Based on different parameters, based on different environmental conditions, and based on the property of a circuit, we see that the output voltages are changed, right? So this slew rate helps us in understanding as to what are those levels. Okay. Fine. So the next one is, so you can think that, it is maximum rate at which the output voltage can change. Okay, so this part is important, the output voltage changing and how much of maximum rate. So we can see that, different levels of voltages are attained. When the slew rate is SR, is too slow for the input, distortion results. So whenever, the slew rate is very less, okay, then we can say that the distortion occurs. So what is this distorted output? You can see that you are not able to see a proper waveform, but then you can see that this waveform is fully distorted. You cannot judge the values of its highs and lows, okay, of its crest, right? So figure shows a sine wave input to a voltage follower. As we all know, this is the best example that we can take, or best circuit that we can think of, right? So this voltage follower, so I am giving an input signal here, and that's my circuitry. Okay, so this is my input signal, okay, and then it gets into the circuit and you'll be getting your final output here after the load, okay, once it passes through the load. So we will right now concentrate on now what kind of output that we are going to get. Fine. Now, as you can see here, you're not getting a sine wave, okay, but you are actually getting a triangular wave, a sawtooth wave, right? So to say, it is not a free curve, right? It is not a free curve. So you can see that it's taking some time to reach from this lower point to the upper point, right? So let me just mark it up so that you'll be able to understand. So from this point, okay, to this point, so it's taking some time to reach that level, and again, it's taking some time to actually reach from this level to here, okay, to this level. So you can see that there's a small change, okay, there's a small change in time, and that is called delta t. It is called delta t. I think now it's more visible. So this waveform that you see here in the bold line is your output voltage, okay, and this small change in the voltage that has happened, okay, from this point to this point is called delta V. Okay, delta V is change in voltage, delta T is change in time. Okay, how do I say that it's change in time? Because this point I have measured here, okay, and this point I'll be measuring here, right? So you can see that it's from this point to this point. So I think there's no doubt in this, isn't it? How is it called delta T, isn't it? Yes.
Yes.
Fine. And similar fashion, okay, on the other side we have delta V. Okay, right, we have delta V. So this is the point, okay, and I have another point here. So this totally gives my delta V. Okay, now it is producing a triangular output, okay, so that's important. So why is it forming a triangular output? It is because the op-amp output simply cannot move fast enough to follow the sine wave input. So it is not able to keep up with the input levels. Okay, so slowly it is actually shooting up from one point to another point. Okay, so if you see, whenever you have this free flowing curve, see, that's the major difference between an analog and a digital circuit. Now in a digital circuit, you just go from 0 to 1. You don't know what is between 0 and 1, but in analog that doesn't happen. You can see at every instant of time, okay, at every time constant, okay, you'll be able to see what is the value of the waveform. Okay, so at this point I know that there is some value here, so I'm just trying to tell you the difference between analog and digital. Okay, so here it is not able to cope up with the values of input. So what is happening, it knows that at this point is my input, okay, at this point is the input level starting, and it is reaching a level here. So the circuit analyzes and tells you start from here and then go up to this point, right? So it is like a line is what connecting between two dots, right? So assume that you have a dot here and then you have another dot here, right? So these two dots are just connected. Okay, so that's how your circuit works. And then it comes down, it tells this is my zero line, and then the maximum negative that it can go, and then again it crosses this, and then it goes on, right? So the triangular wave results. Now many times there can be a question as to why there is a triangular waveform even though there is a sine wave. Okay, so when that question is asked, okay, so this whole thing is going to be your answer for that. Okay, so if possible, make a quick note of it. You can mention that it is because it cannot move fast, coping up with the changes in input signal. So hence we get a triangular waveform at the output. I hope this concept is clear. So keeping this delta t, okay, keeping the delta v, and all these values, we will come up with the formula of slew rate. Okay, so you can see that the one in orange is actually the input signal. Okay, and this is showing that it's with respect to ground. You're passing on the input potentials here, and then we have the circuit here, which is in which is in the voltage follower format, right? And then you get the output signal, right? Output signal also, is taken with respect to ground. This symbol represents that it's with respect to ground, and then you get a waveform. Now in your waveform, okay, you can show that it's a triangular waveform. If possible, you can even put it in dotted lines and show as to how the input signal is. That gives you a clear picture as to which is your input signal and which is your output signal. So when I say signal here, signal is referring to the voltage levels. Is that clear, students? Can we proceed to the next concept?
Yes, sir.
Yeah, fine. So keeping these things in mind, okay, we move on and we come up with an equation, right? So this equation is important, and we try to understand as to what this equation is telling us about. Now let's say that the 741 op amp. Now in your subject, okay, mostly 99%, or I can say 95%, we will be studying only about 741 op amp. Okay, and there are different kinds of op amps which are actually made to suit the gains, to suit the output voltages, to suit the level of impedances, okay, which we will be discussing in the upcoming slides this lecture. Okay, so the typical values that a slew rate of a 741 op amp, okay, is actually about 0.5 volts per microseconds. So which means, what do you understand by this 0.5 volts per microsecond? What do you understand? Okay, I will give you a clue. You can refer to this equation. Okay, refer to this equation and tell me what is this 0.5 volts divided by or per microsecond is actually referring to. What do we understand by this?
Sir, is it referring to the speed at which it works?
Speed at which?
The op amp works.
Not necessarily the speed at which, okay. There is a change, okay, there is a change of about 0.5 volts for every microsecond. Okay, so as the time passes by, okay, let me just go back to the previous slide. You'll be able to understand. So as the time passes by, okay, you are seeing that the waveform is actually dropping down, right? So for every certain amount of time, whatever time is given, we have about 0.5 volts. So there is about 0.5 volt difference for every microsecond. Okay, so if I compare from this point to this point, there will be about 0.5 volt difference. Okay, let me just annotate. You'll be able to understand. Now let's say I am taking from let's say I am considering from this point to this point. Okay, now there are two scales here, right? So what are those scales? I have a voltage scale and I have a time scale, right? So this is referring to actually the change in voltage. Okay, so this delta V is what I'm talking about. This delta V is what I'm talking about, right? So if 0.5 volts has to change, it should take about 1 microsecond. That's the meaning. You understood? If I have to see a change of about 0.5 volts, that is delta V, the minimum time that I should wait is about 1 microsecond, right? For every 1 microsecond, there is a change of voltage of about 0.5 volts. Is that clear?
Yes, sir.
Yes, fine.
Yes.
Yeah, so now moving on, the equation is slew rate is equal to delta V naught. Okay, so this is nothing but your change in output voltage divided by time. Okay, so this is your time, which is microseconds, and change in voltage is about 0.5. So these are typical values, okay, for any 741 op amp. So how do I get these values? From my data sheet, right? So let's see a small example here. Okay, when we are studying this subject, linear integrated circuits, I expect that you have a pen, your notes, and the calculator handy. Okay, so that every now and then we'll be solving problems so that it becomes useful for you to understand. Okay, so we have a small question here. For a 10-volt output change, what's the minimum time needed? Okay, so which means I know what is delta V naught, right? And I want to find out what is T here, isn't it? So what can I do? I can just cross multiply, isn't it? I can bring T here, and then I can bring my SR at the bottom, because I know the values of SR, which is about 0.5. So 10 volts divided by 0.5 per microsecond. So can someone please confirm, are we getting about 20 microseconds?
Yes, sir, 20.
Yeah, okay. See, it's very easy to calculate, I will tell you. 10 divided by 1 is 10, right? So which means you have 10 divisions. So again, that 1, if you divide it by half, so it becomes 0.5. So 10 into 2, right? So it becomes 20. So that's the way, easily, if you just want to calculate as soon as you see it, that becomes your answer. Or the other way that you can do is, you can take this 0.5 inverse. So how much is 0.5 inverse? Students, how much is 0.5 inverse? Inverse of 0.5?
So 2.
Yeah, 2. So when the denominator is taken at the numerator, okay, so instead of dividing, you'll be actually multiplying with that, right? So 10 into 2, so that gives you 20, right? So I hope this problem is understood, right? So this is how you apply your equation. Okay, slew rate is equal to delta V naught divided by T. Sometimes T will be given, okay, and we might ask you to calculate what is the change in output voltage. So time, okay, this. So SR is about 0.5. So you just have one unknown, right? So it's easy to calculate. Can we move on to the next concept?
Yes, sir.
Yes, sir.
Yeah, okay. So the next part is frequency limitations. Just have a look at it. I have a graph towards my left hand side. Okay, and just see the graph. Okay, and you'll be able to understand that we have two scales even here across X and Y. So the one is about frequency, and the other side we have the open loop gain, AOL, right? So how is open loop gain calculated? Just to cross check if you have understood the previous concept. How is AOL calculated? Open loop gain.
We input by output.
Okay, output by input, right? Output by input. But is the load considered or not?
It is
Open loop. Open loop refers to not having any load. Okay, so if you have a load, then it becomes a closed loop. Fine. Okay. See, there are many concepts, okay, that you have to keep in mind. AC, becomes a foundational course for LIC. Okay, so whatever you have studied in analog electronics, those concepts will be coming here. Okay, fine. So you can see that, you have AOL across one scale, and then you have about, you have frequency on the other scale, right? So you can understand that, as your gain is increasing, okay, as your frequency is increasing, what is happening to the gain? It is getting reduced, isn't it? Yes or no?
Yes, sir.
Yeah. So you can find that this is actually coming down. Okay. So figure shows the graph of AOL versus frequency for 741 op-amp. Right. The frequency is plotted to logarithmic base, and that AOL falls linearly as f is increased logarithmically. Okay. So f is increased. So you can see that, it is 1, then 10. Okay. So frequency is what? In what terms? Is it in volts, or is it in hertz, or is it in, meters, or is it in seconds? So what is frequency associated with? What's the unit for frequency?
Hertz, sir.
Good. So starting with 1 hertz, okay, and then 10, 100 hertz, 1 kilohertz, okay, 10, 100 kilohertz, 1 megahertz, 10 megahertz. So basically you can see that, it's been multiplied with 10. Okay, as it keeps moving, okay, you can see that it's multiplied by 10. So a rough, estimation that you can see here is that at f is equal to 100 hertz, okay, so we should locate, where is f, right? And we'll be able to understand, how this works. So f is equal to 100, okay, so where is my f? Yes, it's here, okay, at this point. So at f is equal to 100 hertz, AOL is approximately about 80, right? So you should see, where it is actually meeting. So it is meeting at this point, right? So we have about 80 dB. Similarly, for 1 kilohertz, right? For 1 kilohertz, you can see that, it's giving us a value of about how much? 60 dB, right? So what's the difference here between the two? From this point to this point, what's the difference? We can see that, 100 hertz is being multiplied by 10, okay, so it becomes 1 kilohertz. And how much is the drop? The drop is about 20 dB, isn't it? From 80 it's coming down to 60. So we can say that, AOL falls by 20 dB when f increases from 100 to 1 kilohertz. So 10 times increase in frequency is termed as decade. Now this is important, right? So whenever there is a 10 times increase in the frequency scale, then I call it as something called decade. Okay, so decade is referring to the number 10. Is that clear, all of you? Can we move on?
Yes, sir.
Yeah, fine. So we can see that, here from 80 dB it's coming down to 60 as the frequency is increasing, right? So at one point of time, this has to come down to 0. Okay, so we will just look into it as to when it is going to be 0. So we should keep increasing, okay, and then at one point of time, okay, at 800 kilohertz, okay, we can see here that it's becoming 0. Now there is another concept called octave, okay, octave. Now we calculated based on the 20 dB, right? The rate of fall of gain is said to be 20 dB per decade, right? Why is it called per decade? Why is it per decade? Because 100 was seen previously, and then I multiplied with 10, So it became 1 kilohertz. So for every decade, how much is the gain? The rate of fall is about 20 dB, right? It was 80 and then it became 60. So the difference between them is 20. So 20 dB is the fall that is happening for every decade. Now, what is a decade? What is a decade? We saw that previously. Yes, what is a decade?
So we multiply the 10
Frequency. Yes, the 10,
Yeah.
the multiplying factor. Right?
factor. Yes.
Yes. So we have seen, what a decade is. Right? So there's another concept, as I was mentioning, okay, which is called octave. Okay. So just like how we refer to, certain amount of voltage changing for certain amount of time. So if we are talking specifically with numbers, then 0.5 volt change with, for every 1 microsecond of time. So here we can refer to, an octave concept. Okay, so this is stated as 6 dB per octave. So what is an octave? 6 dB reduction in gain each time the frequency is doubled. Okay, so whenever you see that the frequency has doubled, say from 100 hertz, it has become 200 hertz. Okay, so you can see that there is about 6 dB of difference. Okay, just like how we saw 20 dB for every decade. Okay, so here we can see that, there is going to be a change of about 6 dB for every time the frequency is doubled. So two important things: what is octave, okay, and what is decade. Okay, so these two things you'll have to remember. So decade is something referring to the number 10, right? So which means it's referring to the frequency, and octave is referring to 6 dB. Okay, so with decade you have to associate 20 dB, with octave you have to associate 6 dB. So 6 dB of reduction in gain each time the frequency is doubled. Okay, fine. See, whenever I hear the term double, I always remember Moore's law. Have you come across Moore's law? Anybody? What does it say?
We came across it, sir, but I don't remember.
Okay, fine. So Moore's law states that, every 1.5 year or 18 months, okay, so the number of transistors that was used 18 months ago is going to be doubled. Okay, so let's say 1.5 year back, I had prepared a chip, manufactured a chip, and that had about 100 transistors. So post 1.5 year, okay, I should be able to see about 200 transistors, right? So the number of transistors in each IC are actually doubling every 1.5 year. So that was the prediction given by Gordon Moore, and that very famously is called as Moore's law. Now, why is this happening? This is happening because many things are getting integrated, right? Just take the example of your calculator. If you can recall, previous days calculators, they did have all this integration, differentiation. Okay, you can even um, uh, have logarithmic calculations, matrix calculations. All this, was it possible with previous calculators?
No, sir.
Not at all, right? You major had probably about 4 functions, right? Addition, subtraction, multiplication, and division, with a big display, right? But these days, you have something called natural display, wherein, it shows you the numerator and the denominator. It shows you the matrix, right? It shows all the rows and columns, right, for the matrix calculations. So, things have become very, user friendly, and things have become very, what to say, very good, because, we see that technology is upgrading, okay, because these number of transistors are actually increasing as the years pass by, right? Every 1.5 year, these transistors are increasing, and since the transistors are increasing, the functionalities are also increasing. So that's a boon of technology, right? What is the bane of technology? We get addicted to it, right? So any technology for that matter, okay, it can be your tablet, or it can be your computer, or it can be your laptop, okay, or any electronic gadget for that matter, right? Of course, it's very interactive, the UI is good, okay, so you tend to be with that for a long time. So these days, there's a term that has come up, and that's called screen time. Have you all come across that term?
Yes, sir.
Yeah. So it can be referring to televisions, or it can be referring to the time that you spend on your cell phones, or the time that you spend on your tabs, or or any electronic gadget for that matter, right? So there's a boon, there's a bane, and things, you should take things in a way which you are intended for, okay? So anything overdoing is not good, okay? It should not be too less, or it should not be too more. It should just be the right amount of usage for any device, right? Okay, so we have learned the definition of decade, and we have seen that it has been associated with 20 dBs, and octave is referring to the frequency getting doubled. Okay, so if you can see the graph that we have here previously, which I've put up in my slide, okay, so you can see from 10, probably if I look up for 20, okay, so this is 1 hertz, this is 10 hertz. So if I look up for 20, the value that is here for 10 and 20 should have an approximate difference of about 6 dB, right? Now when I see with the 100 and probably 200, okay, so the levels of these gains should have a difference of about 60. So that is referring to octave. So I hope this is cleared with all of you, right? Okay. Now,
Yes, sir.
AOL falls to 0 approximately for about 800 kilohertz. Okay, so you are seeing that this AOL, okay, drops down, okay, to about 800 kilohertz. So that is practically seen. Okay, practically. Sometimes what will happen, theoretical values wouldn't match with practical values, right? So because there are a lot of practical things that impacts the performance of a circuit. It can be the temperature, okay, or it can be the input signals that you're giving, the resistances that are involved in these sources, so the internal resistances, and the type of connectivity that you give from your supply to the circuit, okay, the type of wire that you're going to use, okay. Basically most of the time copper is used, but then gold is actually a better conductor. But do you think we can use gold for everything? Can I use gold for everything, for the connecting wires and all? Is it possible?
No, sir, not possible.
Not possible, right? Because it's going to be too costly for me, okay. Not only about the cost, but there can be even thefts, right? So keeping this in mind, most of these cables, okay, basically it's about the cost, it's about the money factor. So if I want to keep things under control, okay, but still have some performance, okay, which is not too bad, okay, so I will come up with the usage of copper wire lines, okay, right? So when internal gain equal to or greater than 80 dB is required. Now let's say we have designed a circuit, okay, and I want the circuit to have a gain of about 80 dB, okay. So now let us go back and see, somewhere 80 dB means, okay, I should have the circuit working say between 1 hertz to 100 hertz. Are you all with me? Yes.
Yes.
Yeah. Okay. So why do I say 100 hertz? Because my specification says that I should have a minimum gain of about how much? 80. So I cannot go beyond this frequency of operation, because as I go beyond this, what's going to happen? My gain is going to drop down, and my purpose of having 80 dB, is it happening? Is it happening? Am I fulfilling this 80 dB of gain? Not possible, right? So I have to restrict my circuit for its operation between 1 Hertz to 100 Hertz, right? Okay. Several other op-amps maintain substantial gain to much higher frequencies than 741. As I was mentioning, I told you that 741 is not the only IC, only op-amp, right? So we have other ICs which are tuned, okay, to have higher levels of gains. Okay, so you should just keep in mind that op-amps are not only 741. Right. So moving on, we have a small problem here. Okay, calculating the limitations. Okay, the frequency limitations. Now I hope you have understood, about this operation of frequency up to 100 Hertz when I want 80 dB. Is that clear, students? That concept?
Yes, sir.
Yes.
Yeah. Okay. So I am having a target of 80 dB. So which means I cannot go beyond 100 Hertz. So I'm restricting the frequency of operation from 1 Hertz to 100 Hertz. Right. So there's a problem here. Take out your calculators and put in these values and tell me if you're getting about 1.2 volts per microsecond. Okay. So before that, we will just look into the details and we'll see how we are going to solve it. An op-amp circuit is to have 10 kilohertz triangular output. Now keep in mind, we have seen why we're going to get triangular output, right? The inputs are in the form of sine and the outputs are in the form of triangular waveform. So the reason is because these are not able to catch up with the levels of changes that are happening with the input voltages, right? Okay. So we have about 10 kilohertz is the frequency, okay, and the voltages, okay, the input voltages is about 12 volts peak to peak. Okay, so what is peak to peak? Can someone tell me what is peak to peak? You have done your practicals as well, isn't it? AC lab, you would have seen a lot of peak to peak problems.
So the voltage levels from one peak, like the complete cycle.
Yeah,
of
the
one
complete
side.
cycle. So when I say peak to peak, it's
Positive
referring to,
and
yeah, positive and the negative, right? The maximum values that it can attain, right? Good. So peak to peak is about 12 volts and calculate the op-amp minimum SR. So SR is nothing but slew rate. So we know that, because of the sampling theorem, okay, we choose a frequency about 2 times, right? So frequency and time are inversely proportional to each other. So I want to find out time. So time is equal to 1 divided by 2f, right? I have the frequency, which is 10 kilohertz, right? So am I getting 10 microseconds here, students? Yes, are we getting about 10 microseconds? Someone quickly calculate and tell me, use your calculators. Yes, are we getting?
Yes, sir.
Yeah, okay, fine. Then we know that the formula for slew rate is what? Changes in output voltage divided by time. So time, anyway, we know that, it's here, right? So this value, we just bring it down. And 12 volts is already here with us in the question, right? So 12 volts divided by 10 microseconds. So are we getting about 1.2? Simple math, right? 12 and then you take one decimal, it becomes 1.2 volts per microseconds. Is that clear? Are we getting these values?
Yes, sir.
Yes.
Yeah, fine. So T is already calculated here, right? We have 10 microseconds. So that value, I'm just bringing it down. And, they are telling us to calculate SR. I know the formula of SR. So right now I have just one, value to be calculated, one unknown value to be calculated. Since I have delta V naught from the question, okay, which is about 12, I just bring it down. I put it in the formula, substitute, and I get 1.2 volts per microseconds. Fine. Can I move on?
Yes, sir.
Okay. So the next thing that we'll be looking into is op amps. How do they function as DC amplifiers? Okay. So all this while we have seen the fundamentals of op amp, right? How is it in inverting configuration, non-inverting configuration, and we have also solved a couple of problems. We have seen the impedances, right? And then today we saw slew rates and frequency limitations. So moving on, we'll be looking into how these op amps act as amplifiers, specifically DC amplifiers. Okay. So the first thing that we'll be looking into is direct coupled, okay, voltage follower. Direct coupled voltage follower. Now we all know the term voltage follower and we know what it means, right? So what is voltage follower?
The output follows the input.
Right. So whatever input is given, the same thing comes across the output, right? So this is possible because of this op amp's property based on the inverting and non-inverting terminals and how they try to match up between them, the plus and the minus terminal, and how they try to make the differences to be zero as much as possible. Practically not possible, but then they try to make it as much as possible with the help of either internal circuitry or with the help of external circuitry, right? So the op amp may be connected. Yes.
Get back to the problem we did, because now I'm not getting the 10 microseconds like for the starting. I'm getting it as 5.
Yes, sir. I'm also.
Yes, sir, it's 5.
How much are you getting?
5 microseconds.
Five.
5 microseconds.
Yes, sir.
Yes, sir.
Let me just calculate. 2 into 10K. I think it should be 50 microseconds, isn't it?
Yes, sir, 50 microseconds.
Yeah, 50 microseconds. Yeah. So you take a 0 and then the -6, you will get a proper -6. So once you have a -6, then it's going to be 50. Yeah. So most importantly, I have seen that there are few calculation issues. That's why I always tell students, please confirm if we are getting about these values, because that's the observation that I have seen in the third edition of David Bell. Okay, but anyway, we need to know that this is the formula, how it is substituted, and what values that we are going to get, right? Okay, that is our motive. So which means the whole value changes here. Okay, we bring 50 here. Okay, and the value of slew rate also does change, right? So how much is it? 12 divided by 50. So we should be getting about 0.24. Are we? Are we getting about 0.24?
24.
Yeah. Yes, no? How much are we getting?
0.24.
Yeah, 0.24. See, it's simple, right? See, 12 is already there. Okay. So instead of 10, you're going to put 50, leave the microsecond, leave the volt because it's already here. Okay. Volt per microsecond. So you're just going to do 12 divided by 50. That's it. So 0.24 is going to be your value. And, this volts is here and per microseconds is also here. So which means you have to just divide 12 by 50. Okay, fine. So 0.24 microseconds, what do we understand by this? 0.24 volts per microsecond. For every microsecond change of time, there is going to be about 0.24 voltage change. Okay, what voltage change? Is it the input voltage change or the output voltage change? It's going to be the output voltage change, right? Because we have delta V naught, right? So change. Now we should get back, to the definition, right? What is slew rate? Slew rate is nothing but the maximum rate at which the output voltage can change, right? Is it clear, students?
Yes, sir.
Yeah, fine. Okay, so we've seen the problem. Okay, so yeah, moving on to the amplification part. Op amps as DC amplifiers. Okay, Pawan, thank you for bringing up the doubt. Okay, hope it's cleared now.
No problem.
Yeah, so DC voltage follower. So we are all very much familiar with voltage follower, right? The output is following the input. Okay, and op amp may be connected to a function. This is actually referring to a function generator, okay, that we generally use as voltage follower with or without the use of external resistors. So we can either use a resistor or it will have its own resistor, the internal resistor, right, the functional generator. So we'll be relying on the resistors which are there already inside. So we have learned these formulas, right? I think we have learned this input formula, right? Input impedance. Have you come across this formula? Yes. Have we come across this formula? ZI? Yes or no?
Yes, sir. Yes, sir.
Okay. In which topic have we come across this? Did we
So
solve
the
anything?
fourth module, feedback networks, I think.
No, I am talking about our subject.
Sir,
LIC.
impedance.
Impedance, input impedances. Remember, we used the
Yes.
formula and then we had taken the value of beta. How much was taken, the value of beta? If you can recall, flip back your notes, your sheets, and check what was the value of beta that we had given in the problems.
80, sir.
Beta was generally taken as 1.
Yes.
Right? Okay. Fine. So this is your input impedance, output impedance. Take a note of it. Okay. So it's dependent on the input resistance 1 plus gain into beta. Okay. Beta is the characteristics. Okay, characteristics of your op amp. Generally, we take it as 1. Z naught is equal to R naught. Okay, the output resistance divided by 1 plus AOL into beta. Right. The voltage follower has a very high impedance. Now we have seen the property of an op amp, right? It has very high impedance and a low output impedance, right? So in fact, an op amp is nothing but following the concept of voltage follower, isn't it? So which means the property of an op amp is nothing but the property of an voltage follower. Okay. So it has a low output impedance, and it is used to convert high impedance source to a low output impedance. So this voltage follower can also be used as a converter. What kind of converter? Converter to change the level of impedances. Okay, what kind of impedances? If a circuit, okay, has very high impedance and I want to convert it to a low impedance, okay, so in that point, okay, in that situation, I'll be using an op-amp, okay, a voltage follower circuit, and that will help me in converting high impedance to low output impedance. So it's acting like a converter. Okay, so if I connect, okay, if I connect an op-amp and a voltage follower, okay, so it can act as a buffer. Okay, it can act as a buffer. Generally, what is a buffer? We have discussed this in a previous class, isn't it? What's a buffer? What is a buffer? Whatever you give at the input side, the same thing is going to come at the output side, right? Okay, so it acts as a buffer between high impedance source to a low impedance load. Okay, so this is referred to as buffer amplifier because voltage follower is also functioning like a op-amp. So I hope you have taken note of Zi, okay, and you have taken note of Z0, Zi and Z0. Okay, so these two are important. Fine. Why are they important? Because we'll be solving problems based on them. Okay. Now let us see, this circuit here, okay, which is direct coupled voltage follower. So I have two sections here, okay, figure A and figure B. Okay. So figure A is only referring to, the source, okay, the signal source, the voltage source, and then it has a resistance RS, okay, series resistance RS, and then it has a load resistance RL, okay. So RS is about 6.8 kilo and RL is about 12 kilo. So ultimately, if I want to find out the voltage across my load, okay, then this is going to be my formula, isn't it? So I hope you have learned all this in your network analysis, right? VL is equal to, which is load voltage, is equal to Vs, okay, which is the source into RL divided by the total number of resistance, okay, the total amount of resistance, which is 6.8 plus 12 kilo ohms. Fine. So figure shows the fact that a signal voltage is divided across RS and RL. So whatever signal that gets generated here, okay, so you can see that, this signal, as it passes through, from one point, from this point to another, it comes here to this node, and then it comes from here to here, and then from here, okay, to here. So as the signal passes from one point to another, it is getting distributed across two resistors. Okay, so what are those two resistors? You have RS, okay, and you have RL. Okay, so this is one resistor and this is the other resistor. Okay, two resistors. So I hope this part is fine with all of you. In figure B, now let's come back to figure B. Okay, figure B, the voltage follower presents its very high input impedance to the signal source. Okay, so that's the property of an op-amp, right? So what I'm doing here is I'm just bringing the op-amp in between. Okay, so you can see that 6.8 is already here. Okay, and yeah, 6.8 is already here. Okay, then 12 kilo ohms is already here. Okay, so the only thing that I am trying to do here is I am trying to bring in the op-amp. Okay, so I am making it fit in between the input and the output. Okay, so you can see that the values are the same here, right? Vs is there, Rs is there, you have RL, everything is there compared to A. Okay, so now I'm just inserting an op-amp in between, and we're going to check as to what is going to happen, right? So what is the property of an op-amp? You see that, you know, these op-amps do have high input impedance, okay, of voltage follower. So because of which, what is happening, it's eliminating any significant loss of a signal. Okay, now one thing, students, you should understand, when I say high input impedance, what do you understand? Is it blocking the voltage or is it blocking the current? If you are clear with this question, then understanding linear integrated circuits shouldn't be a problem. So what is high input impedance? What is it blocking? Is it blocking voltages or is it blocking currents?
Current, sir.
Very good, right? So when I say high input impedance, it's not allowing any current. Okay. When I say low output impedance, it means that, you know, there is very low resistance, so, you know, it can just flow through. Fine. Thank you for that answer. So in figure B, the voltage follower presents its very high input impedance to the signal source. Okay, so what is the signal source? Vs. Since Zi is normally very much larger, okay, what is Zi? Zi is your input impedance. So this section is very large. Okay, so let me just put it here. Yeah, so this section is very large. Okay, very large than Rs. Okay, so this value Zi is actually very higher than Rs. Okay, so this series resistance. So there is virtually no signal loss at this point, and effectively all of the voltage levels appears at the op-amp circuit. Okay, so this resistance Rs is very low, okay, and Zi impedance is very high. Okay, so basically you can understand that all of the signal, okay, when I say signal, all of the voltage levels are actually going to pass through, and, you know, there is not going to be any flow of current. Okay, so I hope till this point you all are clear, right? Can I move on to the next concept? Yes. So this is called a direct coupled voltage follower. Okay, so I am having my levels of inputs here. Okay, Rs and RL are my resistances, and then I have my op-amp which is connected in between. Okay, fine. So we have a formula now, okay, where we can say the output voltage, how it's related to input, and you know, the open loop gain. Okay, so the output voltage from a voltage follower output is V naught is equal to Vi, whatever input voltage you gave, minus V naught divided by the gain. Okay, so please make a note of this formula. So this formula is important. Okay, you will have to make note of it. Right, so we know the formula now. The output is very much dependent on, you know, the input voltage, and that is subtracted with the values of V naught divided by AOL, open loop gain. The voltage can be thought of as being divided across RL and the voltage follower output impedance Z naught. So you know, we can see that, you know, it is just as good as a voltage follower. Remember the two R1 and R2 which we used to take. So this is like, you know, actually having a voltage divider. Okay, so one of the resistances is RL, and you know, the total output impedance. Okay, so that is referred to as Z naught. Now we know that, you know, what is the values of output impedance? Is it low or high? Okay, so we have seen the formula. Okay, the output voltage which is equal to Vi minus V naught divided by AOL. Fine. So the output voltage can be thought of as being divided across RL and the voltage follower output impedance Z0. Okay, so which means you have your resistance here, okay, RL, and you have your total output impedance here Z0. So taking these into consideration, okay, you say that it has a very low, especially the Z0 is very low output impedance. So Z0 is normally much smaller than any load resistance. So ideally, our output impedance is 0, right? So very low output impedance, and any resistance, even if I put about 10 kilo ohms, that becomes very much larger compared to Z0. Yes or no, students? Right?
Yes, sir.
Yeah. So thereby, because of this, there's not going to be any signal loss, and virtually all of Vi appears as V0. So this is nothing but called your voltage follower, right? So whatever is at the input side, the same thing should be, coming across the output, but provided there is going to be a gain. Okay. Fine. Now let's see a small example. Okay, and as usual, I want you to clarify and check if the values are proper or not. So we are using the same circuit which was there previously. Remember, we had A and B. So this circuit is what we are going to use for the purpose of problem. Now remember, this circuit was just part of the circuit, isn't it? Part of this B circuit. The only thing that is differentiating between these two is that I do have a voltage follower circuit here, but I do not have it here, right? So we will be using this circuit in solving the example. So just for the sake of simplicity, I've brought it here. Okay. So it has a 1 volt signal. Okay, so you can just make note of the given values: 1 volt signal and 20 kilo ohms load. Okay, 20 kilo ohms load, and you need to calculate the load voltage, okay, which is nothing but VL. Two cases are there: when the load is directly connected to the source, and when the voltage follower is between the load and source. Okay, so there are two cases: when the load is directly connected, okay, to the source, and when the voltage follower, okay, so that means we are referring to both, okay, with and without. So when this load is directly connected to the source, that means without the voltage follower, and when the voltage follower is between the load and the source. Okay, so if you can bifurcate, or if you can differentiate, okay, so this is going to be your input side, and this part is going to be the output side. So we are trying to connect with regards to A. Okay, it is actually connecting from here, okay, to here directly. Okay, so this is my case A, and case B is as usual, the whole circuit here. Okay, so two cases. So I hope you have understood the problem as to what we are supposed to do. Yes. Fine.
Yes, sir.
So we can see that here we have VL is equal to, okay, whatever is the load voltage. Okay, we have seen that it's about 1 volt, and into RL divided by RS plus RL. So we have that formula here, right? We have that formula. So we just substitute the values, and RL value we have it as 12, right? RS is 6.8, and again RL is 12. Please calculate and tell me if we are getting about 638 millivolts. Take your calculators and check and let me know. Yes, are we getting the value?
Yes, sir.
Yeah. So it's correct, isn't it? Fine. Now we will go with the next case. Okay, next case is, where we need to have these typical values. We need actually the values of AOL and RI, because we are going to use the formula ZI is equal to RI into 1 plus AOL into beta. Okay. Now, do you think we have the values of all of these? RI, do I have? No. Okay. So I need to take the typical values, which means I have to refer to data sheet and take those values. Okay. So taking those values into consideration, okay, it's about 2 mega ohms RI, and AOL is about 200,000. Okay. So remember, I was mentioning to you about beta, the value of beta. Okay, we are taking it as 1. Okay, so please calculate and tell me if we are getting it proper. Is it 4 into 10 raised to 11 ohms? Yes, are we getting?
Yes, sir. Good.
4 into 10 raised to 11, right? Okay, so this value is also right. Now we need to find out, okay, what we need to find out, calculate the load voltage. Okay, calculate the load voltage. So ultimately, if I know what is my input levels, okay, so the same thing is going to come across my output level. Yes or no? Yes or no? Is my input and output going to be the different values? Students, can I get some responses? Am I having different values for input voltages and output voltages in considering an ideal op amp? Do we get different values? We do not, right? Because it's a voltage follower. Whatever is at the input, the same thing comes across the output, right? So we have the formula VI is equal to VS, okay? VS into ZI divided by R S plus ZI. So this is nothing but the same formula which we used here, okay? So we have the value Vs is equal to 1 volt, right? It has 1 volt into, okay, the input impedance. Now this is my input impedance. Now remember, this is not Ri, okay, but then it is Zi. So I've seen students making mistakes where Ri means they just put 2 mega ohms here using the data sheet. Don't be in a hurry. Zi is different and Ri is different. Okay, so input impedance you have calculated here with the help of the formula, right? You're taking the values of only resistances. Keep in mind, you're not taking the value of impedance. Impedance you are calculating. Is that clear, students? Yes, are you following?
Yes, sir.
Okay,
Yes,
thank
sir.
you. Thank you, Aditya Pawan. So So we have the value here for no Zi, which is about 4 into 10 raised to 11. So that value is what we are bringing here. Okay, and rs is of course given to us here. It's about 6.8 kilo ohms, right? Plus, and then again Zi, which is 4 into 10 raised to 11, right? So one of you just calculate this and tell me if we are getting about approximately 1 volt.
So we get as 0.9999.
Yeah. So when we approximate it, so it should be 1 volt. Now see the beauty here. If you can observe the question, okay. So what was given in the question? It has how much? It has how much? 1 volt signal as the input. Okay, 1 volt signal. Okay, so here now, a 1 volt signal at the output, right? So I have used that here. Okay, VL, I have used that here, which is my load voltage. Now I am calculating the input voltage, right? So the beauty here is, I'm getting the same thing, right? Are you able to follow? Yes or no? Any doubts here? Any doubts? Please ask. So which means our 1 volt is also correct. So both my input and outputs are matching. Any doubts here, students? Please ask. Or is it clear?
Clear, sir.
Okay. So problems at this sort will be given. So one thing here is most of the formulas are all standard. Okay, we had already used this formula. Okay, if you can just flip back your pages, I don't know if you have made note of it. Okay, it's a good habit to make note of of formulas and problems as we discuss them. Okay, so that once you start writing, you will understand much better than just looking into the screen. Okay, so that will show your involvement and you are practicing in fact. Okay, so we have seen this formula previously and we are again using the same formula here and we are putting in the values. So what I'm trying to say here is the formulas are all standard. Okay, so you can see that the load VL. Okay, so calculating the final voltage values and calculating the input values. So keeping this in mind, we understand that how the voltage follower circuit actually works and how it connects. Okay, how in spite of having all these resistances, okay, all these impedances, but still we are able to get about 1 volt for the input and whatever is at the output, which is 1 volt, is also followed, right? So what are we trying to learn here? We are trying to learn that, okay, let me just write it here so that you'll be able to understand. So I am trying to say that this is at 1 volt. Okay, so since this is taken as a feedback, okay, this becomes 1 volt. And what happens to this here? Here, what is happening to this point? What is happening? If it is 1 volt here, the same thing is tried to follow. So I am going to get 1 volt even here. Okay, both the inverting and the non-inverting terminals. Is that fine, all of you? Okay, so moving on. Okay, so we'll be learning the difference between voltage follower and emitter follower. Okay, so of course our concept of discussion is only about voltage follower, but then I thought, fine, let us have a small comparison between both of them, the voltage follower and emitter follower, and we will see how best they stack upon each other. Okay, so towards the left hand side I have voltage follower, and towards the right hand side I have emitter follower. Now we can see that both can act as a buffer. Okay, now what is a buffer? As I mentioned previously, what's a buffer? Do we get different things at the input and output? Aditya, at the input side and output side, do we get different things in a buffer?
No, sir.
Okay, thank you, Atul. So both voltage follower configuration and emitter follower configuration can act as buffer. Okay, fine. The voltage follower has a very high input impedance and a very low output impedance than the emitter follower. So this is the concept of op-amp, right? Op-amp is having nothing but a voltage follower concept. And here the disadvantage is that DC voltage loss due to the transistor base emitter voltage drop. So there can be a lot of voltage loss. Why is that? Because it does not have high input impedance. Okay, so greater loss of AC signal voltage than voltage follower because of the lower input impedance, right? So this is important. You should you should probably make note of this, and that's the reason, that's the main difference between emitter follower and voltage follower. So these two main differences, if you can analyze, okay, if you can remember, then you can build up your answers based on these 2 points. Voltage follower has a very high input impedance and very low output impedance than emitter follower. So which means the emitter follower has the reverse properties of this. Okay, so it has a greater loss of AC signal than the voltage follower because it has lower input, here high input impedance, here low input impedance, and high output impedance, but then here it is low output impedance. So it is just the opposite to each other. So here the DC voltage loss is almost insignificant, right? Because our output impedance is almost zero, right? So there cannot be any loss. So this is a circuit, okay, differentiating both. The voltage follower, of course, you can draw an op-amp, and then plus VCC, minus V, and then the resistance, and Z0. Z0 is nothing but the output impedance, RL, okay, and we see that the output voltage is equal to input voltage, VI. Okay, so what kind of configuration is this? Is this an inverting or non-inverting configuration? Yeah, students, is it inverting or non-inverting configuration? This circuit that you see here. Yes, are you all there?
Non-inverting.
Yeah, very good. So this is a non-inverting configuration. So here you can just have a look at the emitter follower, right? We have input voltage, okay, with respect to ground, and then VBE, base emitter, RL, okay, the load resistance. So it is nothing but VI minus VBE, VI or input voltage minus VB. So this voltage minus this voltage is what is going to be coming across RL, which is nothing but your VL. So any doubts, students, with the concepts that we have seen so far? Have you all understood the concepts? Anywhere, any point of time, any problem that you didn't understand, or any formula that you didn't understand? Anything that you want me to repeat? Is it all fine?
All fine.
Okay, So just keep in mind, okay, what is meant by voltage follower, okay, and how is it better than emitter follower, okay. It is just the opposite. Keep in mind, it's just the opposite. Then how to apply the formula, what kind of values to extract from data sheet. I've seen many times, data sheet will be given and students will be searching what data to extract from the data sheet. Okay, so very intelligently you should be able to pick up resistances values, okay, the impedance, if in case they ask the gains, okay, if you need it in the formula, then you can take the gain values, okay, or slew rate, okay, for example, if it's not given, then you can take about 0.5. So these kind of, so ultimately, if you know the formula properly, okay, you will be able to find out as to exactly what you need to extract. So what's the best thing to do whenever something is told, okay, probably at the end of your notebook, okay, maybe leave some 10-15 pages, okay, at the end start writing the formulas and what it actually is used for, and what is Ri, what is Zi, okay, what is Rs, what is Vs, okay. So start writing these, and just before your examination, okay, you can just flip across these formulas so that you don't get confused, okay. Suddenly for output impedance, you might put your input resistor Ri, but actually your Z0 is actually dependent on what? Is it dependent on input resistance or output resistance? The Z0.
Yes, sir.
Yeah, the output resistance, right? R0. So like this, if you can, make a note of the formula and what they mean, so it is going to help you during examinations, right? So these were the things that I wanted to convey in this lecture, and I hope all of you have understood these concepts. Okay, just as I mentioned, make note of everything, and it will be useful for your own internals and examinations, right? So we will catch up in our next session, and we'll be looking into a different dimension of inverting, non-inverting, summing, and difference amplifiers.
Yes, sir. So can you update the